Hi there everybody, this is Mike Poirier and I'm going to be doing a Logger Pro tutorial on the most basic and essential features you need to know for your DP Physics course or your DP Physics internal assessment. So this is a completed graph. This is going to be the goal to do over the tutorial. And you might be able to see down here at the bottom, our goal will be to create a data set, talk about manual and calculated columns, learn how to plot uncertainties and error bars, how to do automatic curve fitting, or what we call the line of best fit, how to set up the axes properly for a clear view of all your data, and then how to do a manual curve fitting for your max and min lines so you can talk about the gradient and the Y-intercept, which is very important for the analysis portion of any DP physics investigation or IA. And last, maybe just a couple quick things on formatting for export, if you want to export your graph to a Word doc, a Google Doc, or to an Excel sheet for that you can do further processing or publication later. So this graph is looking at current and voltage, and the gradient for this would be resistance. So volt per amp, or that would also be ohms. And you notice here, the key features is we have a data set on the left, which has my IV current, my dV, my dependent variable voltage, and I'm in this case using a percentage uncertainty for my current and a absolute uncertainty for my voltage. You can see that by the error bars are the same when we go across, actually they aren't the same. The absolute value uncertainties are slightly different here for my delta V, 34352, and then you'll notice my percentage uncertainties for current, they grow slightly as the current gets larger. 5% of, for example, 2 amps is a lot smaller than 5% of 10 amps. So you'll notice that increases the horizontal error bars as well. Okay, so let's make a new one and go from the beginning. We'll save that one. Okay, so this is what a basic Logger Pro graph looks like when you first open it up. Not much is going on at all. We have to add all of our data. So the first thing that I like to do is I will just drag, you can see those little blue squares. I'll just drag that over so I can get enough columns, and usually you'll need at minimum 4 columns, so that should be enough space. And we're going to have our 2 variables, current and voltage. So I just double click on the data set. I'll call it current, shorthand is I, and the unit is amps. Done. Double click on the y-axis. This will be voltage, shorthand is V, and the unit is also V. So just keep that in mind when you're using, say, a quantity like voltage where the symbol and the unit are the same. Just got to be mindful of that as well. And now we're going to add 2 more columns. So if you were to calculate a column, say an average, then you'd use a calculated column. In our case, we already know what the uncertainties are for my data, so I'll be using a manual column. So I'll create 1 new manual column, and I'm going to call this my change in current. So I'm going to use Greek letters here. Greek letter delta, so it's the 4th one down on uppercase. And I'll go delta I. I'll call the shorthand also delta I. And the units here, this is going to be a percentage uncertainty, so I'll just put a percentage to remind myself that. Data will be numeric. And done. And then I'll do one more. I'll go to data and new manual column. Do the same thing for delta V. So Greek upper delta V, shorthand will be the same, and units in this case will be volts, so we'll do an absolute uncertainty for this one. And now I'll plot in all the data. I just did some basic 2, 4, 6, 8, 10, and we're assuming this actually is your final process data, so this is from all of your trials. If you've done, say, 5 changes of IV, 3 trials for every dependent variable, these would all be your average values that you'd be plotting for an investigation or an IA. There we are. And now I'm going to add all of my uncertainty values. In this case, I'm going to say that this is all 5%. And I'm going to say that my absolute uncertainties were slightly different for each average. So just to have some variety. And there we go. And so what you'll notice right now is our graph goes from 0, 0. And you'll see my data points, every 2 amps, my voltage is increasing by 5. So we have a nice linear plot here, nice linear curve or straight line. But the error bars haven't shown up yet. I just have points. It's just a scatter plot. So what we have to do now is we actually have to tell my data set for current and voltage to use the appropriate columns, delta I and delta V, to add the error bars. This is really done really easy in Logger Pro. This is a really difficult thing to do in Excel and in Google Docs, and as far as I know in Google Sheets, for example, you can't add horizontal error bars. So Logger Pro really makes this easy for any DP student. So double click on current, go to options, and when you want to add an error bar, you just got to click on error bar calculations. That's the important piece. And for current, we're going to use a percentage uncertainty, and it is a constant 5%. So I could just write 5% there, but I want to use the column for delta I. Done. And yes, we're going to use that. And there you have it. Now, one nice thing about using a whole column is, let's say, for example, for some reason, let's say that one was 10%, that data set. And I'm just going to auto do this. We'll talk about this in a minute. There we go. There's all my data. You'll notice if I start changing one of these, that error bar is going to grow or shrink dramatically. Very small. These are all the horizontal error bars. So I have a lot of control over what my error bars and how they'll display. Let's do the same for delta V. That will be my vertical error bar. So I'll double click on voltage. Again, go to the options panel and then error bar calculations. And I'm going to choose the column delta V. Done. There you have it. So those are all my error bars. So I have my delta I, or my current horizontal error bar, is slowly increasing by 5% each time. And of course, current's growing, so my horizontal error bar will grow proportionally by 5%. And then I have a variety of error bars that are either the same, 3 volts, so 2 of them are the same, or some are a bit smaller, 2 volts, some are a bit larger, like 5 volts. There we have it. So that kind of covers the first bit with data tables. The next thing we want to talk about is we want to talk about curve fitting. So we want to be able to plot a line of best fit. This is really easy to do in Logger Pro, especially if it's a linear trend line like this. One thing you can do is you can click on this button up here. That'll do it. And I just clicked on that button that has a kind of a straight line, and it plots your linear fit. So this would be my linear line of best fit. And it's telling me my slope is 2.5 volts per amp, or 2.5 ohms. And my Y-intercept is 0, goes right through the origin. My correlation is 1, so basically this is a perfectly linear relationship based on the data I have. Now this is really useful, but right now it doesn't take into consideration at all the error. So in fact, we don't know if this is exactly true, just based on the data we got lucky maybe. So we actually have to also plot the max and min lines as well. And that's what we call our manual fit lines. So I'm going to show you one more way to do this. First, the linear fit. You can do that, or you can click on the Analyze menu, and then from Analyze, you can click Linear Fit. That's really useful if it's a straight line. If you have a quadratic fit, or it's another type of polynomial, exponential, logarithmic, radical fit, then you'd have to choose the appropriate option. So now that we have this, let's go ahead and add a max and min line. What we want to do is you basically want to take the very top of the error bar on one end and the very bottom on the other end to get what could be possibly the maximum gradient based on the data I have. So to do that, data, new model, we'll fit something. I'm going to fit it there. Okay. Actually, so we were fine. So what we're going to do is we're going to double click on manual fit. And the important thing is we want to say enable line drag. And that will mean we can physically move this line around. And appearance, this is my maximum. So I like to pick a color that is kind of maximum, whatever you want to call that. So I'm going to pick something like violet, something purple. Okay. And so now I got a purple line. And so now what I'm going to do is I'm going to line fit. Now, it depends on your computer. For me, it doesn't like to show me it doesn't like to update automatically. So I have to click back and forth between the data sets sometimes to refresh the page, which can be a little bit annoying, but we'll try and do our best here. And we're going to get it as close as we can. That's pretty close. We'll use that. So you'll notice the slope now for this one is 3.083. It's a bit more. So we have a higher slope. Our gradient is a larger value. And that's because we picked the bottom error bar of the first data set and the top part of the error bar of the second. So it's a steeper gradient, steeper slope. So that's telling me that probably the maximum value for the resistor in this experiment that would have happened is around 3, theoretically, based on the error bar, or experimentally, based on the error bars that are there. So now we want to do the same thing for the min line. So to do the min line now, we're going to do the exact same thing. We'll go to Analyze, we'll go to Curve Fit or Model. I'll go to Model. This time I want to do a linear one. I'll say 1 as well. It's going to add a line, and I'll drag that box down, double click on it, enable line drag again. That's very important for this. And appearance, I'm going to change the color this time. I'm going to change this one to blue. A dark blue color. Okay, this will be my min line. And now for my min line, it's going to be the top error bar of the first and the bottom of the error bar of the second, or the last point. And this one takes a little while to do right as well, so you just got to be patient. Takes a few tries. It's getting there. One more. That's good. And of course, if this was your IA, you'd want to be very technical about it and choose everything correctly as best you can. And there we have it. So let's look at what we have here. So my line of best fit is telling me that the resistance of this resistor should be 2.5 ohms or 2.5 volts per amp. The maximum value possible based on the uncertainty of the measurements, the systematic error and the random error and all that error propagation you would have done in your data set, is telling me that the resistor would be approximately around 3.083 ohms. Now, we don't know if it's that many sig figs. So in fact, you can actually change that. Maybe the number of sig figs is only 2. Then it'll do that for you automatically. So you just changes it to 3.1. So let's do that for all these. Let's say, for example, in this scenario, these are all 2 sig fig answers. And we'd expect you to do this as well if this was, say, for your IA. You have to know your number of sig figs or decimal places so it's consistent with the measurement tool that you were using. So resistance could have been around 2.5 ohms. The max value is around 3.1, and the min value is about 1.9. Another interesting thing to look at is the Y-intercept. So in this experiment, this is Ohm's law where V equals IR. We expect that the line should pass directly through the origin like it does in this simple example. But with the error, it's saying that, it could be somewhere between a Y-intercept of 3.9 volts when the current is 0, all the way down to negative 4.2 volts when the current is 0. We know that doesn't make really any sense. If the current is 0, the voltage should be 0. So that's evidence to suggest there's been some systematic error. However, the origin is within the boundaries of those two values. So in your analysis or in your interpretation, there's many things to discuss when you have this type of data that we're looking for when we're grading an investigation or internal assessment. Okay, the next thing we want to do is just do some formatting here so we have everything the way we like it. This graph is actually looking pretty good. You can change where you want the axes to start from. So if you go down to the bottom, it'll change to a little XXX dot. If you click that once and you click on More, you can then say exactly where you want this to start and end. So my x-axis data, I'd like it to go to maybe -5, and I'd like it to finish at about 15. Okay, there we go. And then I can do the same with my y-axis. There we go. And then for my y-axis, I want the bottom to also be -5, and I want the top to be about 30. And I'm going to hit OK. There we go, that looks good. And the last thing I can do is I can add a label to my graph. So this is a current versus voltage graph. Let's see, this is determining resistance, current versus voltage graph. Okay. Again, sometimes I need to click back on the data set and then back on the graph for it to display. It might be working different on your computer. And that is a pretty complete graph. Then while you have all this data, you have the slopes for the maximum inlines, you have all this data, you have the slopes for the maximum inlines, you have your slope, your gradient for your line of best fit, you have the Y-intercept data for all three of these lines. Now you can do further analysis graphically and then interpret them with maybe literature values or other experimental data, get percent error, percent difference, and then continue on with the analysis and evaluation of your investigation. Okay, the last thing to mention is you can always export these. So you can always go export as, you can export in different ways. You can also even just copy this. Sometimes what I'll even do is I'll just take a screenshot. So if you're on OS X like I am, you can just go Command Shift 4, and then you can highlight, Command Shift 4, you can highlight the entire graph. It takes a screenshot of it, and then you can use that in your report. You can just kind of copy and paste that in as well. So there's many different ways to do it. That one usually is the easiest one to do. All right, so that's it. Let's see how we compare to the old graph. I'll just kind of open up the recent one. I'll save my current one. I'll call this YouTube. And here's my current one again. So pretty similar in terms of what we did before. So we talked about creating a data set, talked about manual and calculated columns, but we kind of focused mainly on manual columns. How to do uncertainties and error bars, how to do curve fitting and manual fit, how to set up the axes and some labeling, and then also what you can do for formatting and export. I typically just take a screenshot of the final graph and add that into whatever Google Doc or other type of word processing program I'm using. So I hope that helps, and all the best on your DP Physics investigations. Bye-bye.